Hello, everybody. This is Miss Peachy from your WCA physics class, and we are looking at Unit 6, Lesson 9, Momentum Portfolio today. So you guys have a replacement portfolio for what is in the lesson for this one. So I put a lesson modification in here. You should see that as a little flag showing that there's a message, a lesson modification. Um, on the Student Hub, this video, hopefully you found the link for this video here on the Student Hub as well. And then right below the link to the video, there's also going to be a link to a student worksheet for you to do. So all of that information is both in the lesson modification and is also on our Student Hub. So that is what you should be using for this physics portfolio here at Wisconsin Connections Academy, okay? So we are looking at momentum, we are looking at impulse and Newton's third law in this lesson. And the original portfolio was asking you to do a bunch of research on seat belts, and then you were supposed to kind of design like a seat belt and then carry out some experimentation with it and kind of see how that works. It was just a bit tricky, and sometimes I find that students have a difficult time finding supplies and stuff like that. So while good in theory, might be more difficult to do on your own. That is why we are doing the lesson modification today. So we are going to be using a resource known as PHET. PHET is from um, University of Colorado, and they have a lot of really good resources, a lot of very good simulations to simulate different science concepts. Specifically, they do a lot with physics, but they also do stuff in other genres of science as well. So we've used them before. We will be using them again. They do a really nice job. So we are going to be looking at the collisions um, simulation. So I've given you the link here. This is actually the sheet, the worksheet that you will be filling out. So it looks like this, kind of gives you a picture of what the PhET application looks like. We are going to be looking at both an elastic and an inelastic collision. Start off with an introduction here explaining um, momentum and also explaining what impulse actually is and the impulse momentum theorem, which is what we're learning about in this unit. So momentum is a kind of a property of a moving object, right? And it is related to its mass and velocity. So if an object is in motion, the faster it goes, the more momentum it has. The more massive it is, the more momentum it has as well. It has to be a moving object. Unlike inertia, which we talked about before, which just is dependent upon the object's mass, that does not have to be a moving object, right? So that could be, you could have inertia, or you have inertia can be something that also occurs at rest as well. So momentum, mass times velocity here. The unit for momentum is kilograms meters per second. Kilograms is mass, meters per second is velocity. So basically you're multiplying those two units together. And then it brings into play impulse. So we're specifically looking at collisions when two objects collide with each other. And you think about when a collision happens, that the time over which that collision occurs is also very important, right? And I like to use the example of dropping a raw egg. If I drop a raw egg, it's moving at a fairly fast velocity. The farther it falls, the faster the velocity. So the higher I hold that egg up, the faster it's going to be when it hits the ground. And therefore, it's going to have more momentum. So the momentum of that egg is dependent upon the mass of the egg and how fast the egg is moving. Despite the momentum, if I can slow down the egg prior to its actual collision, so if I reduce its velocity right before it collides, or if I slow down the time it takes for that collision to occur, I can actually reduce the force that's applied to the egg, so the egg won't break. Normally, we would expect if you dropped a raw egg, it's going to smash, right? It's going to make a big mess. Miss Peachy knows this because somebody egged her car this weekend, which she's really, really mad about right now. There were a bunch of smashed eggs all over my car. Obviously, those eggs did not have their velocity slowed down before they hit the car. So one way we can do this is instead of dropping that egg onto a hard surface, we can drop it onto something that's soft, like say a mattress or a pillow or something. That pillow will literally slow down the egg right before it collides, kind of increasing the time over which that collision occurs. If you increase the time over which the collision occurs, then the force applied to the egg is less than it would have been otherwise. And so impulse is force times delta t. So if I have a very, very small delta t, then my force is going to have to be much larger to be able to equal the change in momentum. You're changing the momentum. It's going from a very, very, whatever the momentum is, to no momentum because it's colliding and stopping, right? So the change in momentum is equal to the impulse. If I increase that delta t, if I make it much larger, like I add the pillow, then the force is much smaller. So force times delta t is still the same number, but the force is much smaller because my delta t is larger. Again, still equaling the change in momentum, right? So that's how impulse relates to momentum. So the two types of collisions we're looking at here are elastic collisions and inelastic collisions. Elastic collisions are collisions where two things collide and they kind of bounce off each other. And they typically move separately after the collision and in opposite directions. When we look at momentum, the conservation of momentum theorem applies. That means that the total momentum prior to the collision is going to be equal to the total momentum after the collision. Specifically, we're looking at the total momentum of the system, not the momentum of each individual object that is involved in that collision. So while if two vehicles collide or something like that, their momentums will change, the momentum of both of the vehicles totaled together prior to the collision will be equal to the momentum of the total two vehicles after the collision as well. So we write this down as P total, the total momentum, is equal to the initial momentum, is equal to the final momentum. It doesn't change because it's conserved, right? The initial momentum is the momentum of our first object plus the momentum of our second object. So object 1, we call that the momentum is m1 v1, the mass of object 1 times the velocity of object 1, added to the momentum of object 2, m2 v2. So you do your two little products and you add them together and you come up with a sum, which is our initial momentum. That is equal to m1 v1 final. What's their final velocity times m2 v2 final? So what is their velocity after the collision, right? That's our elastic collision because, again, the objects, they hit each other, they bounce apart, and then afterwards, they're two separate objects still. With an inelastic collision, what you have is after the collision, the two objects will stick together and kind of behave as an individual or like a combined object. My nose is itchy, sorry. So afterwards, it looks a little bit different. Our initial momentum is still calculated the same way. We take the m1 v1, one object, mass times velocity, times the object of the mass times velocity, of our second object. That's our initial momentum. But afterwards, we add the masses of the two objects together because they're now stuck together and they're moving together, so there's only one velocity. So we take the combined mass, add them together, take that times the velocity of the combined unit, and that becomes our final momentum. And again, the expectation is that would be equal to the initial momentum because, oh, itchy nose, sorry. Law of conservation of momentum. All right, anyways, so moving on down to the simulation here. It's going to take you to this website. It's going to take you to this website here. This is our collision lab. You are going to click on Explore 1D. We're going to open this part. So we're only going to do collisions in one dimension, so basically in a straight line. So think of two cars colliding on a road, right? It's not about moving up and down. It's just horizontally. So we have our two objects here, objects 1 and object 2. And there's some settings that we can control. So let's first look at what you need to do here, because it's going to ask you to set a few things. You need to select velocity, select reflecting border, select momenta diagram, make sure elasticity is set to 100%, and make sure your sound is turned on. Just make sure the sound is turned on your computer. All right, so momentum, I have velocity, reflecting border, momentum diagram, and it said make sure sound is turned on. Okay. So that looks like this then, right? You kind of see this. And then before you even begin, you are going to do some initial calculations. So you're going to fill in these empty boxes in this data table using the equation for elastic collisions, right? So you have the initial mass of object 1, which is m1, and its initial velocity, which is right here. You have the initial mass of object 2 and its initial velocity, right? So you should be able to figure out P total by knowing that information. So we just need the initial stuff at the moment to figure out P total. So I have all this information, I get my total momentum. Then I use this total momentum to figure out my final velocity V2. Because remember that the initial velocity is equal to the final velocity. So if you know the initial momentum, excuse me, is equal to the final momentum. So if you know the initial momentum, you can figure out anything in there. Sometimes it gives you that number and sometimes it doesn't. Sometimes it gives you the final readings, but not the initial ones. But that's okay too, because you're just basically filling in the missing information. Hopefully that's all pretty self-explanatory there. If you have questions on how to fill in the missing parts of this data table, let me know. But remember, you're using this set of equations up here. That essentially, this combination of initial stuff is equal to the final, which is equal to the total. So again, if you need me to walk you through that one-on-one, send me a webmail. We can meet in my virtual classroom, but I'm hoping it's fairly self-explanatory there. Now that you have that, you're going to try to verify that information experimentally using PhET. So basically, you've done your calculations already, and you're going to try to see, do they hold true using the application? So we have all the initial stuff now. Now we need to go into PhET, and we're going to plug this information in here. So I'm just going to do a quick split screen just so that we have everything side by side. I'm going to quick do that a little bit better. So essentially, we're going to click on more data. And for our first one, we know the mass of object 1 is 1. So we're going to change object 1 to a mass of 1.0. We know the mass of object 2 is 1. So again, we're going to change that to 1.0. We know that the initial velocity of object 1 is 1. That's actually already set here. We know the initial velocity of object 2 is negative 0.5. That is also already set. So we can go ahead and hit the play button, and we can allow these two objects to collide, and then we can pause it before they have a second collision. That's important. So I'm going to hit play, allow them to collide, and then I'm going to pause it because they've collided with each other. Now they've, just like elastic collisions do, they've ricocheted off one another and gone in opposite directions. And now I'm going to pause it so that I can get now their final velocities. See, that's what I want here. I want to be able to see if their final velocities match what I expect their final velocities to be. Okay, and I want to make sure I set that correctly initially. Oh, so we have our final velocity here. We did not calculate our final velocity, so that you're going to calculate that first, and then you're going to see, does it match what I expected it to be? And you're going to need to calculate the total momentum of the system there, okay? So that's pretty much what you're going to do for all of this. You're going to run every single one of these sims, and then you're going to see if they match. Okay, so then you're going to go to step 7. It said make some predictions. What happens when a moving ball hits a stationary ball of equal mass? What if the stationary ball is heavier? What if the stationary ball is lighter? And then you're going to test those predictions. So stationary means non-moving. So you're going to just use the simulation to kind of play with these different scenarios, make predictions, and then test your predictions using the sim. And then in part 2, you're going to repeat this whole thing with inelastic collisions. So in this case, we're going to go and you're going to reset it, and you're going to go to completely inelastic, right? That's the big change here. But again, you're pretty much doing the same thing you did for the first part. You are going to start by completing the table. And remember that we are going to still use this set of equations, except our final equations, instead of being, you know, M2 V2 plus M1 V1 final, we actually combine them together and do the final velocity times M1 plus M2 combined, right? So you're going to do that. You're going to complete all your predictions first, and you're going to test them as well, the same thing you did for the first one. Then you're going to actually go to more data, and you're going to fill in this information and see if that holds true. Do they hold true the same as you would predict? Okay, and then it just happens, says on the left side of the screen and directly below the impact area, the total kinetic energy of the system is displayed. I think you have to actually click it right there. So this is slightly different. You click on kinetic energy. It says total kinetic energy here. Okay. Run a couple of setups in inelastic and elastic mode and note what happens to the kinetic energy in an inelastic collision and in an elastic collision. And then you need to hypothesize of why there's a difference. And then finally explain how your observations in both parts 2 and part 1 really demonstrate the law of conservation of momentum. So that is what you're going to be doing for this portfolio. It is 16 points. You're going to complete this lab worksheet and submit it to me. And, that's pretty much it. If you have any questions or difficulties, please contact me via webmail. Otherwise, guys, good luck. I think it's going to go pretty well. And, have fun.